So this is 11-4. We'll split it in 2 days, normal distributions. It's one of my favorite things in statistics. I absolutely love it. One of the reasons I love it is because it talks about this concept of percentile rank, which, as near as what I can tell, is nobody on Facebook understands percentiles. I cannot tell you how many times every fall or spring when test results come back that I see parents brag about their kids on Facebook. So I see parents brag that their little angel tested in the 23rd or 24th, let's go 24 since I have typo, 24th percentile constantly. Now, this is not something you brag about. You need to understand that. If you're talking about testing data, this is not something you brag about. You don't. You shouldn't be. Now, I guess everything's relative to the past performance of the child. But not only do parents brag about this, their friends start bragging. And no one tells the parent otherwise. Even I don't do it. I don't say what I want to say. Hopefully, you guys will not be on Facebook bragging that your little angel tested in the 24th percentile. That's information you keep quiet. And you keep that quiet and you try to fix the problem because you have failed to some degree as a parent. Your kid shouldn't be testing in 24th percentile. Let me tell you what 24th percentile means. 24th percentile means you are better than 24% of all who took that test. That's not necessarily a good thing, because what that means is you represent the bottom 24th percent. That's what you represent. So that means that 76% did better. All right? We don't brag about things like that. We're not supposed to. I don't understand the bragging, things like that. It means you do not understand percentile rank. You think that's good. It's not good. It's not good at all. Are there things that you want to be in a lower percentile? Yes. It might make sense to be in a lower percentile of weight because Americans by and large are overweight. So maybe being in the 30th or 40th percentile on weight is a good thing. Height is not a good thing unless you just enjoy being short. You want to be in the upper percentiles. You might want to be 90th, 99th percentile, something like that. But you need to understand percentile. It tells you how you compare to others. And generally speaking, the higher the better. So make sure you understand what a percentile is. All right, moving forward, how can you use the normal distribution to explain where data values fall within a population? This is called the empirical rule. It's also known as the 68, 95, 99.7 rule. And it tells us how data lies among the mean as far as standard deviations go. So we're going to denote the mean by the Greek letter mu, that's the letter mu, and by the standard deviation sigma, that's sigma if you forgot. And if you are within one standard deviation of the mean, you contain 68% of all data. If you are within 2 standard deviations of the mean, you contain 95%. If you are within 3, you contain 99.7. Now, in your little text box right there, you need to write some stuff down. It's the words. You need this. Write it. It does only apply to normal distributions. If you take enough samples, you can normalize about everything. There's a couple of things you can't, but the key is take enough samples. And there's ways that statisticians can normalize data. All right, let's fill out the empirical rule. So since 68% lies within 1 standard deviation, these equal areas account for 34% of the curve. They are 34% of this curve's area. Sometimes people write this down as 0.34, which is fine. Lots of people do. If you're within 2 standard deviations, you account for 95%. So let's take the 68% that we've already accounted for. Let's do a little mental math. Let's go old school because you haven't done this in a while. I can't do 5 minus 8, but I can make this a 15, right? And I would borrow 1 from that. 15 minus 8 is 7. 8 minus 6 is 2. 27% between these two equal areas, okay? So I cut it in half and I get 13.5%. Each of these equal areas represent 13.5% of the bell curve, or as a decimal, 0.135. It's really up to you what you want to use. I don't really care. All right, now we're going to go out to 3 standard deviations. 3 standard deviations is 99.7%, and I've already accounted for 95%, so I take away my 95%, and this I can do 4.7%, which I have to cut in half, and I get 2.35%. And again, some people use decimals. They would say 0.0235, 0.0235. It's really up to you, whichever one you do. And then we have what I call the tails, this tail and that tail. So if you think about the curve extending on out, you would account for 100% of the curve. You take away the 99.7% that you accounted for, and you get 0.3%, which you cut into 2 easy pieces that each contain 0.15% of the data, or 0.0015 is a decimal. I actually use the percentages here as opposed to the decimals. When you see me do this stuff, I'm going to be thinking about percentages because it's easier to work with the percentages than it is the small decimals. I don't know why your textbook chose this example, but they did. An example of an early application of statistics was in the year 1817. A study of chest circumference among a group of Scottish men exhibited an approximately normal distribution. Their chest circumferences ranged from 33 to 48 inches, with a mean chest measurement of 40. Why study Scottish men's chests? It's such a weird thing. And a standard deviation of 2 inches. Use the empirical rule to help you understand the distribution of chest circumferences in the study. What range of chest measurements contains the 68% which fall closest to the mean? Now, anytime you do an empirical rule problem, you need to draw. It will help you memorize the rule. So I'm going to draw a bell curve. That's what it's called. It's called a bell curve or a normal curve. I don't know why your textbook chose symmetrical curve, but they did. So the mean is given as 40, and the standard deviation is given as 2. So 40 plus 2 is 42, and then 38. If you just look back, you'll see that these 2 pieces are 34% of your data. If I take away another 2, I'll be sitting at 36. If I add another 2, I'll be sitting at 44. And these guys account for 13.5. If I go out another 2, I'll be up to 46, and I'll be down to 34, and these guys were 2.35. The tails are each 0.15. There you go. There's your bell curve, kids. All right, what range of chest measurements contains the 95% closest to the mean? That's going to be the stuff within, oh, I forgot to do the first question. First question is 68%. That's this stuff right here. Chest measurements that fall between 34 and 42 inches. Sorry, 38 and 42. The 95th percentile is where we go out 2 standard deviations. So it's going to stop at 44, and it's going to stop at 36. That's going forward and backwards 2 standard deviations. So between 36 and 44 inches. All right, the 99.7 is going to be 3 standard deviations. It's all the way out, 34 to 46. All right, what measurements represent the 3/10 of a percent farthest from the mean? So that was the math done here. That was these tails that are 0.15% apiece. So when I answer this one, though, I've got to say things that are less than or left of 34 inches. So less than 34 inches and greater than 46. And not a hard concept. The only hard thing about the empirical rule is memorizing the bell curve. That's really the only hard thing about it. I still don't know why they did a men's chest measurement example, but whatever. What would you expect the chest measurements to be for the 2.5% of men with the smallest chest measurements in the population? So one of the reasons kids struggle with this is just they have no number sense. I do know that, and I'm just drawing this to make so I don't mess up the other one. Boy, that was a bad curve. I wanted smallest, right? That's going to be over here. That's something's wrong with me today. I know that there's a little guy right here that is 2.35, and there's a little guy right there that's 0.15. And I know that 2.35 plus 0.15 is 2.5. It's going to be these two pieces right here. That's what I'm interested in. Specifically, I'm interested in this data value. And I'm going to be less than or left of it. So that data value is 36. And the answer to this one is less than 36 inches. These are the guys with the smallest chests, which I guess is a perception of weakness. All right, what would you expect the measurements of the 16% of the largest chests in the population to be? So a couple of things I have over here is I've got this 0.15 here, I've got this 2.35 here, and then I've got, do you remember? 13.5 there. If you take those three together and you add them up, you get 16. So let's go back to where I finished the curve and let's see what lies there. 42. If your chest is greater than 42 inches in circumference, you are in the top 16%. So I'm looking for chest measurements greater than 42 inches. They represent the top 16%. Not a hard concept. We're almost done. The ACT has a mean of 20.8 and a standard deviation of 5.8. And again, I'm telling you, you need to be drawing. It's how you memorize this thing. But you're not going to listen to me. You're just going to keep doing you. And I've had the same conversation every single year for 10 years. Like, you need to draw. You need to draw. I don't care who you are. I don't care how highly you think of yourself. You need to draw. That's how you memorize the bell curve. I mean that. I really don't care who you are. I don't care what your last name is. I don't care if you think your poop don't stink. It does, by the way, because it's poop. You need to be drawing. Everybody who's ever memorized this thing has drawn it repetitively. That's just what they do. We have a mean of 20.8, and we have a standard deviation of 5.8. So I'm doing 20.8 plus 5.8, which is 26.6, I hope. It seems legit to me. If I do 20.8 minus 5.8, I get a 15. These guys each account for 34%. That's a really bad looking 3. I'm going to add 5.8 again. I'm going to get 32.4. Remember, this is 13.5%. I'm going to take away 5.8, and I'm going to get a pretty sorry ACT score. Oh man, it's bad, of 9.2. Right now, we have accounted for 95% of the data between here and here. Remember that? We're out 2 standard deviations. I got to go another standard deviation out. And remember, these guys were each 2.35. And we're about to get a score on the ACT that I've never seen. I've never seen a score this low. But I'm sure it's possible. We're looking at 4.2, 3.4. That poor kid. This one's going to have to stop at 36. The max score on ACT is 36. That's the max score. And 32.4 plus 5.8 is 38.2. So we're going to stop that one at 36 because it's just not going to get any better. And the ACT test is not a good one to do this with. But it is what it is. And I have to omit this question because this question doesn't make sense in this context. In its place, let's say 2.5%. Okay? All right, what scores represent the bottom 2.5% of all ACT scores? I really need to redo these questions. I just don't like them. But anyways, they are what they are. The bottom 2.5% is going to be these guys. Scores less than 9.2. And I have seen some scores that have been a 9 before. It's pretty rough, man. I don't know if those kids got a diploma or not. They shouldn't have, but they probably did. The top 50% is pretty simple. That's going to be this stuff over here. It's greater than 20.8. This is actual ACT data. And the top 2.5% would be scores above 32.4. That's where you want to be, right? You want to be in that top 2.5%. That's where you want to be. Of course, a lot of you guys are going to be thrilled to get to here. That's really, really good. That's if you get a 27, look at that. A 27 is top 16%. That's awesome. Like, you're going to go to college most likely, and you're going to do well. Of course, the thing about college is most kids there are also pretty smart too. They scored 27 or higher by and large. Recent SAT scores for college-bound seniors are normally distributed with a mean. There's SAT, which is used on the East and West Coast colleges. A mean of 508, standard deviation of 121. How does the empirical rule help you understand the performance of individual students? What proportion of students receive scores greater than 387? So again, we just draw the bell curve, and I know that you don't want to listen to me, and you're almost done listening to me. We have a mean of 508. Let's go out of standard deviation. These guys are 34 and 34 respectively. So if we take away 121, I'm evidently too tired. We will get 387. If we add 121, we will get 629. If we add it again, we will get 750. And the SAT tops off at 800. So this is a little funky, but whatever. If we add it again, we get a score that doesn't matter. I don't think I need to be too worried about this because I want greater than 387, which is everything to the right. So there's a 34, there's a 34, there's a 13.5, there's a 2.35, and then you got that little tail, which is your 0.15. This is one way of doing it. Just add everything to the right. So you got 34 and 34, which makes 68. And these guys we've done before, it's 16. So it's 68 plus 16%. All right? And if you put those two together, you get 84%. 84% of all SAT scores are higher than 387. So if you take the SAT, which since you guys are in Tennessee, you probably won't, and you get like a 380, don't you be going on Facebook bragging. Tell your mama to just shut up. Don't talk about it. It wasn't good. I think that covers it for today. It does, because tomorrow is the Z-score day. So anyways, there's the beginning of the normal distribution notes. I enjoyed it. I hope you did too. See you tomorrow.